Yeah, so hello there, CodeMaker4 here. So remember back in the good old days when we had 8-bit computers, and then suddenly 16-bit computers started to exist and they were much better. And then your grandma probably remembers using some 32-bit computers, which were better again. And then nowadays 64-bit computers are the norm, which are again, the best computer so far, arguably. So clearly, the more bit width your ALU has, as in the larger numbers your computer is capable of doing maths with at the same time, the better, right? Well, what if we just built a 1-bit computer anyway, for jokes and fun? I mean, it's gonna be a very slow computer, sure, but you only need to make a 1-bit ALU. A 1-bit ALU is tiny. So I cobbled together this little joke of a computer. It's called the 1B PC, even though it's absolutely not worth naming a personal computer. And as you can see, it's relatively small. If you exclude the modded instruction ROM here, it's only about 1800 gates. That's including the built-in RAM, which is it functions more like a register file. This is a weird computer. I shouldn't get into it. Actually, I will. There is no ALU. It is so small. It is more or less kind of mixed in with the instruction logic over here. It's a weird computer. So this is my little CodeMaker4 DVD screensaver test using a display that I reused from the SMPU, my latest attempt at making a real computer. So of course, one of these computers is going to be much faster because one of these computers actually has a full-blown 8-bit ALU. Here's the two videos showing side by side. As you can see, it's not even a competition, right? One of these computers is twice as fast as the other. Want to know which computer is twice as fast? This little joke of an esoteric pile of garbage. Yes, my friends, for some reason, this computer cobbled together without any intent of making something useful is twice as fast as my latest real attempt at making a real good computer. So in this video, I'll be going into how this 1-bit abomination works, why it is so fast at this specific demo, what other useful and fun tricks it has up its sleeve, and finally I'll show you a few other things I made related to this, including a compiler and an almost complete emulator. And after that there's even more related to what I'm going to be working on next year. Yay, let's get going. So to get a sense of the speed of this computer, I have these little ToadPod notes over here, and they kind of make sounds every time a new instruction is started. So I'm pretty sure, yeah, this lower tone is whenever a new instruction starts. And that higher pitch is kind of subparts of certain instructions. Yeah, it's a zippy computer, that's true. Most instructions in here are pretty normal. Halt, reset carry, set a register on to a constant value, like the usual stuff, right? And that's where you have a normal computer with a ROM over here. Funny thing on this computer, that's all of the instructions where you usually have multiple bits of data going through at the same time, because it's a 1-bit computer, not an 8-bit computer. Now I could just literally make 1-bit versions of all of these instructions, but I didn't want my computer to be that bad. So what I did is each of the math instructions, they take a 4-bit argument, and that is gonna activate a little internal repeating clock over here, which will kind of repeat the instruction multiple times automatically. So in reality, although the architecture is basically a 1-bit computer, the way you program it, it's more like a variable bit width computer. And that's really cool and weird. Okay, that's cool and all, variable bit width instructions, but how are you going to make variable bit width registers to go with these instructions? Good question. The answer is you don't. This here is all of the memory where you can temporarily store values to do math with. I call this RAM because it's addressed with these 3 address registers. Now these address registers, despite being called registers, they're not registers in the sense that you'd usually use them to temporarily store inputs and outputs for the ALU. The only values in here are values directly loaded from program ROM and the results of incrementing it a few times based on how your program is coming along. All the data going into the ALU, it's directly read from the addresses in these address registers, sent to the ALU, and then directly written to the address of the writing address register. So we have 2 inputs, 1 output. Great, so let's make a little example of how that's going to work in practice. So let's kind of lay out a little memory map here. By the way, if you're looking at the memory, this bottom right corner over here is going to be address 0, then it's going to go all the way up to 15, then we have number 16 over there. It's going to go all the way like that until we have all of the 256 bits of memory we have. And let's say we have a red number over here and a green number over here. And they're both 5 bits. And we want to add them together and store the result in this blue location over here. What you do is you take the address register referring to the first input of the ALU and set it to this value. Then do the same for the second input register, so the middle one. And set it to the start of the second input value. And we set the output register to the start over here. Now, we start our 5-bit add operation. During the first iteration of this add instruction, what happens is these 2 bits are read. They're put into the ALU together with the stored carry bit. And the result is a new value for the carry bit and a value to be stored in this location over here. Then, auto-magically, all of these counters are incremented by 1. So, blue is incremented, red is incremented, and green is incremented. And now, we can do the same thing again. We read these 2 values, send them through our ALU together with the stored carry bit from the previous instruction, and the result is going to be a value to be stored into memory at this new location, and a new carry bit that can be stored over here. Then that little loop I showed earlier is going to automatically repeat this 5 times until it's finished. This is how we can do variable bit width math operations. This is also kind of how we have our variable bit width registers. Even though I always refer to this as RAM, the way in which it functions and the way in which we cannot really use math to determine one of these addresses, they're always results of incrementing values read directly from ROM. This feels and is used in a way that's much more easily compared to a register file, which is the fancy word of just all of the memory of your registers combined together. This is a variable bit width register file by just doing it 1 bit at a time and not caring about their spacing. So, okay, that's cool and all. One of the shenanigans this allows is that, say, we want to do a 100-bit addition. Of course, for our instructions, we only have this 4-bit counter, so we can only do 16-bit additions at a time. But you see, the joke is, you know, these counters are being incremented 5 times for a 5-bit addition. Well, at the end of the instruction, that means that the counters are actually going to be 1, 2, 3, 4, 5. They're going to be 1 bit after the actual range they were supposed to calculate. Which means that you can immediately just start another 5-bit add operation with the next 5 bits. And it'll just continue chugging along through memory like 3 little colored trains. On most computers, you can do this, but you'll have to manually mangle with the carry bit to make sure that the carry output from the previous instruction is going to be given to the carry input of the next instruction. Here, that mechanic is opt-out. It's done by default. And even if you want to opt out, which in practice does happen a lot, carry reset is such a simple and fast operation, it doesn't really negatively impact the speed of this computer. Especially because the program memory is separate. It's a separate ROM. So it's fine that you have to read in another entire instruction. It's really quick. Yeah, so let's talk about speed. So this is a Harvard architecture. So As you know, there's two main ways of building a computer architecture. There's von Neumann, where all of the data and all of the program data are in the same memory space, which means that you could have a program theoretically calculate some new instructions and then immediately like execute those as actual instructions without putting in some emulator magic. This Harvard architecture, on the other hand, is much simpler because you separate the data memory and the program ROM. The entire point of a Harvard architecture is that it's much simpler and thus much faster. This is the main reason the 1-bit computer is faster than the SMPU. Not only was the SMPU a von Neumann architecture, but all of the memory was external, which means that there was a lot of overhead in communicating the timings of the data transfer and making sure you can hook up any slow or fast memory and it'll still work. There's no overhead here. Like, it's just ROM and it's just expected to be fast. There's no communication happening here. I should mention that there's versions of this computer that have this working with totally vanilla memory. I'm just using modded memory here for convenience. Yeah, I think that's mostly it. Oh, wait, there's a compiler. I made an entire whopping compiler. Well, it's half vibe coded. There's way too much code here. I mean, wait, let me turn off the computer. It's bleeping too much. Stop. Where are you? There you are. Great. Yeah, so this is the compiler. It's a Python program. So you use Python, run the program, and give it a source txt. But because I vibe coded this, I added way too many features in here. It will try to nicely format your code with errors. Like, this is not even the nice formatting. This is with everything explicitly squished into a single line. You can have it do stuff like automatically recompiling whenever you save the file, automatically exporting to MTech memory, so you can load it into the game just with one button in game. It's on GitHub. It's been on GitHub for a while. What's also on GitHub is a 90% finished emulator. If you want to go finish that, it's all yours. Go do your thing. It's on GitHub. I'm too lazy. And it's a separate branch, so you won't download it accidentally if you don't want it. I might make a better version of this computer in the future. One thing I really like about the 1-bit computer is that it's really small. And I feel like a slightly more serious attempt could result in a actually really useful computer. I think that's all I wanted to yap. Oh, yeah, I'm getting into scrap mechanic mod making. I might make some fun mods in the future. Yeah, I was busy into mod making with this project 90% finished, so I thought I'll just quickly dump this on the interwebs for you to enjoy. All the files and links are in the description. Have fun. Bye. I guess I still don't have an outro. I mean, I have a beautiful display and a beautiful computer to make an outro in, but I don't know, I'm too lazy. Oh, Merry Christmas, by the way.